Welcome back for another physics lecture. In this video, we will be discussing electromotive induction or electromotive force. We will also introduce Faraday's law and Lenz's law and look at the force on a current loop moving through a magnetic field. Now on to slide 2. First, we're going to look at this experiment. If you move the north pole of the magnet up through the loop of wire as shown, this induces a current in this direction. Once you bring the magnet to a stop, the current stops. If you then begin moving the magnet back down, as in step B, it then causes a current to flow in the opposite direction. If you repeat the experiment as shown in steps C and D with the south pole, the currents induced are opposite to the direction of those induced by the north pole. As shown in E, every time you bring the magnet to a stop, the current stops. On slide 3, we see yet another experiment. In this experiment, when the switch is closed, the galvanometer momentarily registers a current which quickly goes back to 0. When the switch is opened, the same thing happens with the current flowing in the opposite direction. On slide 4, we have something that looks very much like the motor from our last lecture. It is, in fact, a generator. Generators are really nothing more than electric motors run backwards. This is how hybrid cars conserve gas. When you hit the brakes in a hybrid car, you actually engage the engine as a generator to recharge the batteries. So if you ran the experiment shown here, the current would go back and forth as you turn the handle. This and the other experiments led to a couple of discoveries. The first is that the magnetic flux is an important quantity. The magnetic flux is just a measure of the total magnetic field penetrating a surface. For the setup in this picture, the magnetic flux is just phi b equals the magnetic field times the area of the loop times the cosine of the angle the loop makes with the magnetic field. For arbitrary surfaces, we write this as the integral over the surface of B dotted with ds. It is the dot product that gives rise to the cosine in the equation above. From the formula, you can see that the magnetic flux is Tesla times meter squared. We call this a Weber. The EMF, or electromagnetic force induced in the loop, is given by Faraday's law. Faraday's law states that the induced EMF is minus the derivative of the magnetic flux with respect to time. If there are n loops, then this would simply add a factor of n as shown here. The minus sign is a result of what we call Lenz's law. Lenz's law states that the induced EMF creates a current that opposes the change in magnetic flux, i.e., induction opposes any change in flux. In this picture, a rectangular loop of wire is being pulled out of a uniform magnetic field with a velocity v. The area of the loop still in the magnetic field is given by x times L, so that the magnetic flux in the loop is B times x times L. As we pull the loop out of the magnetic field, this decreases the total flux through the loop, since x decreases. The induced EMF is then minus B times L times the derivative of x with respect to time. Because x gets smaller with v, our velocity can be written as minus the derivative of x with respect to time. This means the induced EMF is B times L times V. If the loop has a total resistance of R, moving the wire sets up a current given by the equation I equals B times L times V divided by R. For positive velocity, the flux through the loop decreases with time. That is, there is less and less of the loop in the magnetic field. By Lenz's law, the flow of current is such that it opposes the change in flux. Since the flux is decreasing, this means the induced current produces a magnetic field in the same direction as the external magnetic field. Thus, the current induced as we pull this loop out of the magnetic field flows clockwise. Imagine wrapping the fingers of your right hand around the wire with your fingers on the inside of the loop. Your thumb then points in the direction of the current that produces a magnetic field into the page in the middle of the loop. Another way to look at this is by wrapping the fingers of your right hand around the loop in the direction of current flow. Then your thumb points in the direction of the magnetic field inside the loop. Now let's consider the forces due to the current flowing on each leg of the loop. The forces on the top and bottom legs of the loop are equal and opposite to one another and cancel out. The force on the right hand end is 0 because there is no magnetic field there. On the left hand side is given by the current times the length of the side crossed with the magnetic field. This is going to be a force opposite to the direction of motion. By the right hand rule, L cross B is in the opposite direction to the velocity. Taking in what we got for current before, the force is B squared times L squared times velocity divided by R. The power, back from our kinematic studies, is the force times the velocity, or B squared times L squared times V squared over R. Electrically, the power is P equals I squared R. Again, substituting for I, we get B squared times I squared times V squared over R. This is the same as the result above. This brings to an end this segment on EMF, Faraday's Law, and Lenz's Law.